So, as you might remember from last week, we're now talking about science. So, just to review what we've done so far. In the first week, or the first module, we just went over the basics about arguments and about beliefs. And you probably remember the details. And in the second week, we went over the methods of philosophy. So we talked about intuitions, what those things are, what thought experiments are, and how those are supposed to work. A few different views on how those are supposed to work. Then we talked about skepticism, and in particular we asked, can one be justified in believing universal skepticism? And that week we also considered some self-defeat arguments. So we considered self-defeat arguments in relation to intuitions generally, and then we considered self-defeat arguments in relation to universal skepticism. Questions about this stuff from the last module about methods? Okay. So now we're on to science. So here are some questions we're going to ask, or try to answer at least. You don't need to write these down necessarily, but I'll review them for you. So first, what is the logic of hypothesis testing? So when we're testing hypotheses, how's the logic of that supposed to work? We hinted at that Thursday. Okay, and then given the logic of hypothesis testing, what are we supposed to learn when a hypothesis is successful? Namely, our hypothesis predicts X, and then we go out into the world, do some observations, and we find X. What have we learned? Alternatively, what do we learn from failed hypotheses? So we went out into the world and didn't find X. What have we learned about our hypothesis? And then we're going to shift gears a bit and start to talk about scientific progress and rationality. So we probably all have the intuition that science makes progress. So we think, whatever we used to think about health in ancient times about we should just let people bleed out in order to help them heal. We think that, today's medicine is made progress on that, right? So we realize now that things that we thought were true in the past are probably false, and what we've got now is more likely true than the stuff we used to do in the past. Physics, we think we're making progress in physics, right? We no longer think Newtonian physics is completely true. We think we've got something better. So there's progress, but the question is it rational? And you might think, yeah, of course. We're going to consider some reasons to think, yeah, maybe it's not quite as rational as we think, or not rational in the way that we think it is. We also might think that there's a clear divide between science and pseudoscience. And we're going to try to figure out what that clear boundary is. And then we're going to draw a distinction between experimental science and historical science and try to figure out what the difference is and if that difference matters for, say, whether one of those sciences is superior to the other. So just to give you an example, experimental science is the kind of thing that you do in a lab, right? You have a hypothesis that makes a prediction about the future. Then you do some stuff and see if what you predicted about the future comes true. That's experimental science. And then historical science would be something has happened in the past, and you're trying to figure out exactly what happened. So you make some observations about the world now to draw inferences about what happened back then. So geology is a historical science, right? We're looking at layers of sediments and things like this to figure out, what the past was like. Climate science, in part, is a historical science, right? Because we look at evidence about the past to try to explain the past. But climate science is also an experimental science because we're also trying to make predictions about the future. So it's a bit of both. And you might think that one of these is better than the other. We're going to try to figure out if that's the case. So today, we're going to focus in on these first two questions. First, what is the logic of hypothesis testing? And then what do we learn from successful hypotheses? So last class we introduced what we called the ideal scientific method. It went something like this. In the reading, Hempel calls it narrow inductivist conception of scientific inquiry. I think he also does call it the ideal scientific method. But there's 4 steps. It goes like this. Observe all the facts without bias. Analyze the facts without or before imagining a hypothesis. Induce a generalization from the facts. For example, X causes Y. Do more observation, analysis, and induction to test your generalizations. You all pointed out multiple ways in which we should reject the idea that this is the scientific method. Does anyone remember what some of the problems you all were seeing with this? Savannah.
The ice cream and murder rates example we had, that not all, does not correlate on all the data.
Good, yeah, so if you have really big data sets that have lots and lots and lots of different variables, you will find correlations between those variables that are almost certainly spurious correlations. So the example we used was the correlation between ice cream sales and homicide rates. And this is like a real correlation that was really found. Surely we don't think that an increase in ice cream sales also increases the homicide rate. And surely we don't think that we should reduce the homicide rate by selling less ice cream. So if we observe all the facts via number 1 here, we could get these types of spurious correlations in our analysis and therefore end up with some probably false conclusions. So it seems like 1 is kind of off base. Anything else that you guys remember that we didn't like about this? Yeah.
You can't really force your brain to analyze all those facts before you start imagining hypotheses.
So you're questioning the idea of whether 2 is even possible?
Yeah.
So once we start examining lots and lots of facts, we're probably without even realizing it or involuntarily, we will start kind of noticing patterns. And we might start to imagine hypotheses. You might even think, look, in order to figure out what facts we ought to be gathering, we need to have a hypothesis in mind, right? So it's not like scientists say they're writing a grant proposal, right? They want to get a bunch of money so that they can do some studies. It's not like their grant proposal can say the following: I'm going to observe everything and tell you what I find. No, the people who on the committee who review these grant proposals and decide who to give money to are going to say, no, I need to know what your hypothesis is, because I need to know if these observations that you're going to do are even relevant to your hypothesis, right? So if I fill out a grant application that says, I'm interested in learning if smoking causes cancer, here's what I'm going to observe: cancer rates, smoking rates, people's favorite color, people's favorite style of music, and the color of cars that people drive. You might think, okay, those first 2 things, smoking rates and cancer rates, seem reasonable. You kind of lost me with favorite color, favorite car, or whatever the other variables were. It's not clear to me why those would be relevant to your hypothesis about smoking causing cancer. I'm not sure I want to give this person money to do research. It doesn't sound like they're very good at this. Any other issues you take with this ideal scientific method? So the things that you've already mentioned are the things that Hempel mentions in the reading. He also mentions, so you've mentioned things that he hasn't mentioned, and he mentions some that you haven't mentioned. But some of the stuff that you have mentioned is also the stuff that he has mentioned. So there's some overlap there. And I mention this just to say, this happens a lot in philosophy. You'll read philosophy and you'll think, look, I've already thought some of this stuff. This isn't groundbreaking. You're right, it's not. There are two things to say about that, though. One, it is true that on some level, much of philosophy is just intuitive, right? Why? Because we're often appealing to intuitions, right? And intuitions are usually widely shared. So the intuitions that philosophers have will often, at least sometimes, be the same intuitions that we have as non-philosophers, perhaps. But two, I think it's important not to underestimate how difficult it is to make your intuitions explicit and to put them into the form of good arguments, right? I think maybe when you were writing paper 1, you might have realized that it's a little bit more difficult than you originally realized. You probably thought, I'm going to knock this out, Thursday afternoon. And then at some point Thursday afternoon you thought, okay, I wish I'd started earlier than Thursday afternoon. Or maybe you didn't start that late. So the point is, yeah, not all of these thoughts are original. The contribution comes in making the intuitions explicit and arguing well. And that's the part that seems to be hard. And that's the part that philosophers, are trying to do well and maybe do better than the average person who doesn't study philosophy. Okay, so that's the ideal scientific method. The takeaway here that you all realized last class and that Hempel is trying to get you to realize as well is scientists don't do this. And this isn't one of those things that I know people don't do this, but they should. No, this is one of those cases where it's people don't do this and they shouldn't do this. So it's not just like, well, scientists are fallible, so they don't do this ideal thing that they ought to do. It's like, no, scientists do something else, and they ought not to do this. It would be bad if they did this, for the reasons we've just discussed. So there's two basic types of hypothesis testing we're going to talk about. You can call it like confirmation and falsification or something like that. So hypothesis testing, we come up with a hypothesis, we make some observations, and then we draw some sort of conclusion. This should sound roughly familiar. Falsifying a hypothesis goes like this. If our hypothesis is true, then we will observe something. We did not observe that thing. Therefore, our hypothesis is not true. So that's what falsification is supposed to look like. You guys know some logic. Is that a deductively valid form of argumentation? Remember what you learned about if-then clauses. Zach.
Is this like you can't affirm the consequent? Is that what's happening here?
We are dealing with the consequent, but are we affirming it? Yeah, so the premise 2 has a not in it. It's saying not the consequent. So we have if something about the antecedent. So if our hypothesis is true, that's the antecedent. Then, and then the consequent is we will observe something. And the second premise is saying we did not observe that thing. So it's denying the consequent. Are you allowed to deny the consequent? Does denying the consequent tell us something about the antecedent? Getting some nods, yes. Good. So this is deductively valid. Okay, so from what we've learned about logic so far, this seems okay. Yeah.
So if we were to say we did observe the thing, therefore our hypothesis is true, would that be valid or no?
We're going to get to that in just a moment. Good question, Taylor. So again, here's another way hypothesis testing can go. Again, we have hypotheses, we make some observations, we draw conclusions. here's what confirming a hypothesis might look like. This is kind of what Taylor, I think, was referring to. So again, first premise, the same. If our hypothesis is true, then we'll observe something. We did observe the thing. Therefore, our hypothesis is true. Last class, one of you realized, or maybe a few of you realized, rather quickly, that's an invalid form of argument. It's what actually Zach was just talking about. He was talking about affirming the consequent. We don't want to affirm the consequent. That's what this argument does. The consequent of that if-then clause is we will observe something, and then we affirm that. We did observe that thing. Okay, so, let's say we're early 20th century, and we're dealing with Einstein, and Einstein makes some prediction about a certain type of particle that we should find under certain conditions. In the earliest 20th century, we don't have the technology to find this particle because we can't get particles. We can't find particles small enough or observe them, small particles this small, and we can't get particles up to the speed that they would need to go to make the observation we need to make to find out if Einstein's prediction is true. But Einstein makes a prediction. Okay, so now we fast forward to like 20 something, I don't remember what year it was, 2014, 15, 13, something like that. And the Large Hadron Collider over in Switzerland/France is running experiments, and they're trying to test this prediction that Einstein made many, many years ago, and they find the particle that Einstein predicted. So Einstein had this hypothesis, and he was like, look, if I'm right about things, we'll observe that there is a particle of this nature. Many, many, many years later, we observe a particle of this nature. Therefore, Einstein's right. Why not? Yeah, so you guys are saying this is logically invalid. But I mean, so maybe we don't think his hypothesis is true. But it's not like, are you saying we can't conclude anything from the first two premises? Why did we spend all that money on the Large Hadron Collider if observing this prediction wasn't going to tell us something of value? Maybe it can't tell us that the hypothesis is true, but it can tell us that the hypothesis is something. Go ahead.
But it's not false.
Okay, that's a start. That would be good. So here's what scientists are doing. They're not trying to figure out the truth, okay? I realize that that's maybe too lofty. Here's what they're trying to do. They're just trying to figure out what's not false. So we could draw a big pie chart, and we could be like, here's all the possible hypotheses. And, up to now, we've realized that this many of them are false, and this many of them so far don't seem to be false. And then, here's what scientific progress is. It's like making this chunk of the pie chart bigger, so we can know that more and more of them are false, and conversely, know that fewer and fewer could possibly be not false. I guess it would be more than just possibly not false. But they would be not false, is this. And, we're trying to make that slice of the pie bigger and bigger. And maybe someday we'll get to the point where, we've filled in all of this, and we've got it narrowed down to this final little bit here. And we know that the hypotheses in this little area of the pie chart, those ones aren't false. We've ruled out all these, and that's what we're doing when we're doing science. Does that sound like what scientists think they're doing? Yes? Okay. Who thinks scientists either think that they're doing something else or that scientists really are doing something else? And what might they be thinking they're doing, or what might they actually be doing? Yeah.
I mean, usually they're trying to develop hypotheses, and if through testing them they wind up being false, so be it. But usually, if you're forming a hypothesis, it's out of some idea that it might end up being true if you're going to test it, rather than just seeking falsehoods.
So yeah, the idea here seems to be, look, scientists think they're making some positive contribution other than here's a list of things that seem to not be false. So like, when there's a big scientific discovery and like popular news venues like the New York Times write an article about how scientists have discovered, usually the headline doesn't go, scientists have discovered that such and such a theory isn't false. Like that doesn't seem like a really sexy headline, right? It's more like, no, they've discovered this thing, and then the implication is like, they've discovered that such and such is true, or probably the case. So this is bizarre. We have an invalid argument. Taylor, I think, is right to think that, strictly speaking, all we can conclude is that we don't know that the hypothesis is false. But we seem to think we're doing more than that. So we're going to talk about that a little bit today in the in-class assignment. Hempel talks about this. We're also going to talk about it whenever we read Popper, which I believe is the reading for Wednesday. Yeah. Questions about this stuff before we get into the in-class assignment?